Welcome to this event. We're so excited because today we're talking about a 3D technology, but we're talking about two great applications that we're going to have. I'm Erin Reed. I'm the marketing manager with Polaris MEP. This is what I look like behind the mask. Sorry about that. Habits holding. If you haven't worked with Polaris MEP yet, our goal is to be the resource for Rhode Island manufacturers. As a trusted advisor, we try to help our smaller and medium-sized manufacturers with their top line, bottom line, and pipeline. The way we do that is by either directly delivering services in all of those things you see on the wheel, from sales and marketing to operational improvements, or we connect you to experts who can help solve your problems, help you reach your goals. For example, with R&D or with technology acceleration. And that's really where our focus is today. Want to go ahead and click through? So today we are thrilled to have, standing just off screen, is that it? Hi, Chris. Chris, whose last name I'm going to get, Wilczewski.
Wilczewski, yes.
Oh my gosh, once in a lifetime hit on that. Chris is the founder and CEO of Functional 3D, and we're thrilled to have him as part of our partner resource network here at Polaris MEP. Chris, what will we talk about today?
Hi. Yes, my name is Chris Wilczewski. I am the founder and CEO of Functional 3D, a 3D scanning organization, and we cover a wide gamut of scanning. We focus specifically on the scanning process and consulting with our customers to make sure they get the final result they're looking for. So today we're going to be talking a little more in depth into Functional 3D, a little bit more about myself, and then we'll get into an introduction of 3D scanning for those who are not familiar with the technology, how it works, and what it does. Then we'll talk about quality control workflows. We'll talk about a traditional workflow, probably very common in most of the manufacturing spaces. And then we'll talk about how scanning can either supplement or improve that process. And then we'll get into reverse engineering. So designing, reverse engineering, taking something from the real world, bringing it into the computer, and then creating a digital copy of it. We'll go through the traditional workflow in that case as well, and how scanning is accomplished and the advantages it brings and the value it brings to our clients. And then we will jump into an actual live demonstration of scanning, the quality process, and a small reverse engineering demo as well. So a bit about myself, Chris Wilczewski, as I mentioned, and I've been in and around the tech world for about over 15 years. And the past 6, I've been focused solely on the world of 3D scanning. I previously worked for one of the manufacturers of 3D scanning, Faro Technologies, where I got the opportunity to learn many of the different workflows that our clients used. With that, I was in both the construction space, spent a few years there, and also the design and quality side of things as well. So I got to see the workflows of many different organizations, how it's being used, including even the TV and film industries and video games. So let's talk a little bit about what 3D scanning is, how it's accomplished, and what can be done. So at the very entry level, but can produce some very, very good results, is to use cameras. So just using even your phone camera on an object, taking tens or hundreds of photos around. There's some softwares out there that allow you to put that information together. So once you have all that information together, then what do you do with it? So there's the other pieces of technology are laser scanners. Laser scanners are for typically larger objects. The unit itself will sit on a tripod, spin around, capture everything in a full 360 down to about a millimeter level of accuracy. Great for large construction projects or even things like sailboats, which I'll be scanning in a few days. Finally, I also use, and Functional 3D also uses stationary structured light. So this is a device that uses a projector and camera or cameras to be able to capture a deviation of an object using a projected pattern. So what are the industries supported by 3D scanning? First is going to be historical preservation. We're going to actually touch base a little bit on that in a project I'm working on with Rough Point, Newport, and R&D Technologies in North Kingstown. So being able to easily create a digital copy in both 3D as well as in full color for use in AR, VR applications, a good way to get people interacting. People with visual impairments can now touch objects that they weren't able to touch before. And so there's many different ways that this data can be used to enhance the interpretation and ability to work with historical pieces of artifacts. Industrial design, we're going to be talking about the reverse engineering and design process and how 3D scanning can be utilized there. Architecture and construction, it can be used both on the as-built, so creating a model from what's there accurately and being able to understand that information, as well as quality. So we can take that, the original design, bring it in and combine the data from the real world to make sure that the contractors, subcontractors, everyone did their job correctly and that it's in the right place. In manufacturing, the primary use is what we're going to be talking about, quality today, making sure that what was made matches the design or within the specified tolerance. And then final, film and video games, very similar to historic preservation, being able to create a 3D copy for VFX purposes, for having props, recreating props. Many of those things can be used, being able to have that information digitally and work with it is a common way to help speed that process along. There we go. And here's one of, speaking of movie and VFX. Colored will look different. Not sure why the color is not coming through. My apologies. But this is the submarine, the USS Albacore. I'm doing a scan of this for a documentary. Oftentimes micrometers, depth gauges, angle gauges, number of different manual tools are utilized and then written down by an operator or by somebody in quality control. These are common tools, and they can be, they are very, very accurate in many cases, but often can be tweaked or over torqued or under torqued to produce the value that's being looked for. And so there is an introduction of human error in that process. There's also an introduction of human error when writing down that information. So we have CMMs. These are very, very accurate devices, but they come with their own challenges. They are large. They typically require someone to manage and program them. They are very, very expensive and oftentimes require a specific space or even room, a temperature and humidity controlled room, in order to work and display information, making sure you have someone qualified to be able to run this. And then, of course, like we mentioned, documenting everything, being able to write everything down that's being taken. Perhaps you're using a full CMM, but that could be challenging in itself. And then there's the hope your measurements are correct. You're crossing your fingers. You're just hoping that what was documented, or your team members, your employees, wrote everything down right. Did they take the measurements properly? Did they follow proper procedure and protocol? So that could be kind of nerve-wracking, because you're not going to find out if it's incorrect until it's delivered to your client. At that point, once it's done, it's out, it's ready to go out the door, it's been checked off and signed off on. And so what happens next? You're not in tolerance. It's going to be costly. You may lose customers from this. You're going to be shaking your head. You're frustrated with perhaps employees or by your SOP. So there's many different ways that this can be very time consuming and also a loss of revenue. And so we want to get into what can we use scanning to combat some of that. So one of the first and foremost things about scanning is there's really no hands-on. There's no touching of the part, the device. You set it and press go. So the scanner will turn around a part on a turntable like that, and it will automatically take scans at specific intervals and then use that data in the overlap from overlapping to align the information together. Once you've scanned, you create a point cloud. So you have these points in space, essentially what you would get from, say, a CMM, a lot of information and three-dimensional data that's in the computer system now. And you can create those quality reports from that. You can select and create just about anything you can do with your hand tools. So you can get those inner diameters, you can capture measurements from anywhere, and you can compare a full 3D model in full 3D space without just taking measurements off of one point and using that as a reference. It also is going to be extremely helpful in some of these areas where maybe you're making something that has a complex curvature to it. That would be very difficult to measure with standard tools. This is going to be very challenging to make sure it's within your spec. So some of the, this also allows for automation in the system. That software that we showed right here can be done by an operator. So scanning can be done by one person, saved into a file on a server, and the actual quality report is done on a completely different computer. So all the operator is doing is capturing that three-dimensional information, saving it, and putting it in a folder. It's actually this process right here that you see on screen, this reporting process, can be completely automated. And so it really reduces and minimizes any operator error in that process, and definitely reduces and pretty much makes it go away is any sort of documentation error. Everything is there and it's all documented, and it's just going to be on that printout when it's done. Absolutely.
It seems to me like that's a huge time saver.
Yes.
And when we're all strapped for talented workers, the fact that we don't have to have someone taking hundreds of individual measurements, writing it down, double checking, right?
Yeah. It's a much faster method, and it just reduces so many of those possible errors because of the automation capability of it. And yeah, it's really very user friendly once you kind of get a little bit of a walkthrough on it. And it's basically just set the part on there, press go. And especially if you're trying to get into the level of precision that you would be getting into if you're getting into a CMM, having that space savings, the user savings, right? That's a really tough role to fill if you need someone like that, whereas optical scanning can provide that in a fraction of the time and a lot more pieces of information.
Thank you. Sorry.
No, please don't apologize. Optical quality inspection. So this is scanning of large parts. This is, I believe, in automotive, but this is on an arm. So these, a robotic arm. So these scanners can be combined into a fully automated manufacturing process, and they can be used with multiple as well. So multiple scanners can be used to quickly scan from multiple different angles, capture everything, put it together, and then create that report. So in this one right here, they're doing an automated report for where those foam blocks are. I'm hoping my video is coming across on the excellent. So it's going to show then where things are in and out of tolerance, as well as to what point they are. So now they can be repositioned, scanned again to make sure that they're within their required location. This is another capability is touch probing. Optical can't see through objects, but sometimes you may be able to get to a point via a probe like this. So through this, we use those small dots that are on the probe itself to be able to capture data from within a cavity that you may not be able to easily scan. So this can then provide that information Or if you just need maybe cylindricity, how circular is an object or specific points, this can actually speed it up as well. If there's only key areas that maybe you don't need to scan everything, you can just capture a few points for your quality inspection. And then here's that robot arm, more of a simpler platform for that quality piece. So it has the turntable, a robot arm, and a scanner. And it can then take multiple different angled positions of scans because, again, it can only capture what it can see. These are optical based. Next up is going to be the design and reverse engineering workflow. So very similar in the capture process to quality, right? We're going to be using things like micrometers, depth gauges, etc. We're going to be making notes. We're going to be taking that all down, sketches, maybe some photos if you're in CAD, and you can use that to overlay. But you're going to be limited to single point measurements. So you're taking from here to there, here to there, here to there. It's not all combined in a full 3D manner. So small documentation errors or small measurement errors can compound based on that. And so again, we're going to be documenting everything. Very, very similar to the initial process in quality. We're writing it all down. Again, we're hoping that information is correct. And as I'm sure R&D Technologies could attest, revise and remake. I'm sure they had plenty of customers that they printed almost the exact same part for dozens of times in certain scenarios, making sure that you get the output that you're looking for. And that can be very, very not only time consuming, but costly. And that process it takes a whole lot out of the team when they're continuing to work on the same project. But just finding little bits and pieces that's not coming together right. So how does scanning help those types of applications? Well, you can measure just about anywhere, first of all. On the left, you can see there's a piece that we've done for a mining gravel facility. That's a part for crushing rocks, large industrial piece of equipment. It's a casting, and we did that one with actually our room scanner because of both the tolerance we had, but the size and the location that we were going to have to deal with. We actually ended up dealing with some rain that day, which we had no problem with that scanner. For Twisted Throttle, which is a picture right there, they were struggling to get the dimensions, get the form of the fairing of those plastic parts. These were designed by BMW, and there's no CAD available for them. They wanted a bracket. They had hard mounting points, and they wanted to follow that curvature very closely to make sure their part looked nice. And they had spent, before I came out, a few days working on that and printing, testing, changing, print, test, change over and over again. They'd spent about 3 days working on that process until they finalized on giving me a call. And within an hour and a half, I was able to give them all those surfaces that they could then use in SolidWorks to design around properly. And it worked perfectly the next time. This is a project I worked on with Polaris, actually, is the GoTef. They were looking for a method it was very hands-on process to build in these little peaks and valleys, basically fingers and going over, but it was required and necessary to create this imperfect pattern because of the way that the air circulates through the oven. So they found that trying to do some more traditional methods of making it thinner, rolling it out, creating this kind of pattern just wasn't working and wasn't delivering the result they wanted. So we actually scanned their product on the baking sheet, and we used that to create then a mold that they could use for adding to a roller. So they were able to wrap it in silicone and roll right over and create the pattern that they normally would create by hand, saving them a lot of time. So some really fun and obscure applications that I think many of us would never even think of being needed, but these are definitely ways that the scanning technology right? Being able to measure the peaks and valleys of a oatmeal-like consistency food would just not happen with just about any other method. So this allowed us to do that and produce that that information for them that they could use to create their rolling pin. So we can now not only measure all that information, but we can then model everything that's visible. Again, these are light-based products and scanning. I have worked with some CT scans that people have provided me, so that is possible as well. So this comes out the same way, and that is actually able to get into cavities and information that would be visible. That is not something that Functional 3D offers as a service, but it is something we've worked with data from. And right here, you can see this is that mining part that we created a full CAD model for. And then now we can document that as well. We can create traditional CAD drawings. We can create the standard drawings and manufacturing drawings that would be used for the quoting process, for quality control, many different areas. Once you have it in that CAD space, you can then use that information to create whatever you want to create from it, or around it is another one. And the other final piece is just about anything you do manually is going to be very difficult to reproduce in color, especially organic or pieces of information that might not work, might not come through or project easily if you don't get it perfect. So right here is that sculpture I mentioned. And this is a historical artifact. You can see in that back, there's a crack going down it. For anyone who can see my video, that's all back here. You can see that coming through. There's definitely some, I'm going to guess there were some times where this was glued back together. And so with 3D printing, you're able to take that piece of history and put it in people's hands. That's great for children, being able to touch something. And it's also great for people who have visual impairments that may not be able to see some of these historical objects. So they can actually pick them up, touch them, hold them, and then see them for themselves, as opposed to getting a description or just hearing about it. So being able to experience in that way, I think, is really important and very helpful, as well as just documenting, like you saw, being able to put this in a 3D application. This is the model itself in my presentation right here. This is not a video. This is the three-dimensional information that's spinning around on a virtual turntable in PowerPoint. So it allows for that. And so gives just a different level of interaction. This can be brought in online. As now, we're going to jump into the demonstration piece, and also I'll be going back and forth on anyone who has questions, and I'll be more than happy to answer those as we go along.
Chris, one question
Yes.
that we had received was,
Yeah.
okay, so a lot of our manufacturers right now with supply chain issues are struggling to find parts. And they might have something that's holding up, for example, a production, an order,
Right.
being able to deliver to the customer. So is it too late? I mean, if they get to that point where they just can't get the parts, is that too late to call in somebody like you to help them perhaps 3D scan the existing part, the one they're waiting for, and maybe get a temporary part printed? Or...
Yeah, so I would say, obviously every situation is different, so I can't give a full answer. That's gonna be yeah, sure. But absolutely there are situations, especially if you're sourcing those. And I've run into situations if you're sourcing them overseas. I've seen companies where then your overseas company actually owns the mold. You don't own the mold for some of this stuff. So you may have to then go out and source a different mold, or the mold they made, they'll send you, but they're not going to give you the files on how to make it. It's yours, you own it, but they made modifications oftentimes with plastics, the mold is actually different than what the final part is because of the way that cooling and all that stuff happens. It actually deforms from the mold and can be problematic. So sometimes the mold can be different than what you sent them as your CAD. And so they had to make modifications. So there are many ways that 3D scanning, or the other one is you get the mold, and I've seen it where they want to use it in a different machine, or and this different machine has a different mounting process for that mold. So now you need to be able to mix and match the mold with the old mounting and creating adapters. And the other one is in the world of manufacturing, parts and pieces fail on your manufacturing equipment. And so being able to reproduce those in-house instead of waiting weeks or months for the manufacturer to send you, because they're now running into a supply chain issue. So getting that repair piece that's going to make your machine run, that then now you can produce on, can be very, very big waste of time. So if you can just replace it in-house and have someone print or manufacture the part yourself, and that's even been done pre-pandemic. Absolutely, there's definitely ways that we can have that conversation, understand what the problem is, and see if there's a fit to help move that process forward a lot faster than a traditional method. One of them was the MBTA actually bought a scanner a number of years ago. I worked with them on, and they use it for reverse engineering parts that fail in the field that are going to be a long lead time, but they want these trains up and running tomorrow. They don't want them sitting waiting for this, it's a button or a switch or something that's small and innocuous. They don't want to leave the 3D print in there the whole time, but if it's going to be in there for a few weeks or a few months, not a problem. And so they're able to then get their equipment back up and running and get people to work or whatever else they need to do. And so, yeah, absolutely. There's definitely a lot of ways that this process can be plugged in to a number of different challenges that the modern manufacturing process has.
Exactly. We definitely heard at RSMP that especially as companies who are within the defense supply chain are starting to hear more requests for more frequent and more detailed quality reporting. And so this seems like this would be something that could meet that need as well.
Absolutely. We have, units that get down. My unit is a 0.08 millimeters accurate. It's that's my unit here, but they get progressively more accurate on some of them as well. So there's a number of units that are quite a bit more accurate than mine. That's the one I use because it's a nice middle ground for both from both a cost and a amount of data standpoint. So I get 10 million points per scan image basically from that scanner. So I get a lot of data. It's a high enough quality for a vast majority of what I do, and covers a lot of ground. So, but there is higher quality than that. And I've even worked, like I said, mentioned the CT. I worked on, someone sent me a CT of like tiny, it looked like it was about the size of a tooth. I'm not sure what surgical thing it was. It looked like it also had some bone grafting stuff on the side, and like it had this like lattice structure with, and they wanted that reverse engineered. So I was able to provide them with CAD documentation they could work with. Yeah. Yeah.
And you mentioned the level of accuracy guys have. Do you run into issues with 3D printing being able to match that?
Oh yeah. No, sorry. So yeah. Yes, in your traditional, I mean, anything that's manufactured, there's moving parts. There's always going to be some level of accuracy, and you're going to pay for it, just like in traditional manufacturing as well. The more accurate you need something, the more you're going to pay. And so that's always going to be that. And that's the same thing with machining, any of that stuff. And so oftentimes when you look at a more traditional, maybe machined part. You're going to have some areas that are of a very important tolerance, and then others that are meh. It needs to be close, because we can work around it, or the tolerances aren't that tight in these directions or these areas. Something like, I'm thinking of like a piston from a car. The back side of the piston, it's cast, right? I mean, it's machined on many different dimensions, but on the inside, they don't care. It's cleaned up and it looks good and it works. Like, I'm not worried if there's a part of the casting is not exactly where it should be. So it's very application specific on that. But I think, as far as 3D printing goes, from what I've seen, as opposed to your more traditional FDM, where you're kind of moving around a gantry that's squeezing out filament, but even that can be highly accurate as well.
For those of us who are watching this video later on, you may not realize that all in the room with us, we have Jordan Novak of R&D Technologies.
Say hi.
So R&D Technologies is a frequent partner with Functional 3D, Chris's organization, and also Polaris MVP in finding unique solutions to unique challenges, and sometimes just better solutions to common challenges. So there's a little bit of both of those in the additive systems and the approach that they use. All right, Chris. How do we do this demonstration? Remembering that Casey can always cut this video.
Sure. So I'm going to just flip my camera around so we can take a look at what most of the stuff is going to be on the screen, but at least show you what that process is. Full screen? Sure. I'll stop sharing for just a moment.
There we go.
Yeah. So we've got the scanner right there on a tripod. We've got our turntable right here, and they're already pre-aligned. I set that all up beforehand because the system does need to understand where that scanner is, the turntable is before. So we're going to turn that down like so. And we'll go ahead and we'll put my little demo part right here that we're going to use. And
I'm noticing a few things about your part. It's not entirely solid, right? I've got.
Oh, correct. Yes.
Here I've got.
Yeah, we'll see it in 3D on the full. Okay. Yeah, exactly. It shows, it demonstrates different types of challenges you would need in both the quality as well as reverse engineering workflows. So we're going to go more down the traditional path. So I'm just going to do a single measurement just so you can see, hopefully on screen, those light, the information changing on there. So it is using a pattern. As I mentioned, this is a structured light scanner. This one uses a single projector and a single camera to extract the information that it's seeing. So it projects a set of known images. And what it can do in combination with that turntable is now turn the part around to capture in the areas that it doesn't get from a single point of view. So once we're done, we now have, every program has a different method of moving things around. We can see, oh, actually we can't because I'm not sharing my screen. Try that. Share.
So this is the scan you just made.
This is the one we just took right here. We can see little bits of we can just delete that away and that's gone.
Those were all the plans in that.
No, that was I think that was the turntable right there. So yeah, you can see, as Aaron was mentioning, we've got some recesses. See, we can take off any anomalies, but This is printed on a pretty standard 0.2 millimeter layer height. And you can see each of those ledges there where those layer lines are. So we can really grab in a lot of detail. I've already scanned this part and combined it. I just did one side for our purposes today. Let's go into the quality control. So first and foremost, we've got our CAD model that we did, that I drew up for this. And we've got the scan data here. So now we want to take and align these two pieces of information together. And that way we can create that reporting we were talking about earlier. So we're just doing automated initial alignment. So that gets our data close together. So now we can see kind of how it's overlaying, making sure that we're aligned the way we want to. And then we can do a best fit alignment. And I usually like to oftentimes in manufacturing, I guess I could turn it back on myself. You've seen the part already. This way the microphone's catching me properly as well. Am I centered? I'm not looking. Excellent. Oftentimes in manufacturing or in quality, you're going to have specific areas of that high interest that I was talking about. You're going to have your alignment points. How was it, when it was put into the mill? Where was it held? So you're going to have those pieces of information typically in your spec already. And again, this can all be automated. So I'm just going to pick these 3 planes so that way the part can corner around here. And it's going to slide now. It's going to use those as its primary area of interest. So it's going to use those pieces of information. We're going to hit OK. It's going to take a moment and you see how the data shifted a little bit. So not tried to average everything out based on those 3 planes. As I mentioned, I didn't scan the bottom in, but now we can start to then create our 3D comparison between CAD and the scan data. So we create like a heat map here to show us where we're in and out of tolerance. We can set our tolerance to whatever we want for this visualization as well. So if everything within, say, 1/4 millimeter is fine, we can up that and then see where the values lie now. So we can adjust those as needed. And kind of discussing how good or bad 3D printing is. This is just a consumer level 3D printer and it produces results as such. So we can see how that changes. We see that we align based on this corner right here. There's probably some shrinkage that happened or some imperfect, but that's why I actually like using a non-perfect part, because you can see then from the data where it's off or where it's problematic.